Should I put it here? Oh. Good morning. It's my pleasure to invite you to another edition of Vignyana Patashala. We started this series of pedagogical lectures where absolutely top-end experts come and give a set of lectures which are more accessible to students and would help bring up the new fields into the institute or even enhance existing ones. So it's my great pleasure to invite to have Professor Lakshmanan Sriramkumar, who is a professor, senior professor at Indian Institute of Technology, Madras. I'm looking at a sheet. I mean, you look at a sheet for two reasons. If you don't know the speaker well, or you know the speaker too well. Because in the other case also, there's the danger that you might say things which may not be, the right things to say. So he is one of the leading cosmologists of the country. He's been focusing on the early universe. Prior to that, he had worked a lot on quantum gravity, quantum fields in curved space-time. And of course, cosmology provides the arena for testing all the ideas, and he's been leading a big group. He was at the Harish Chandra Research Institute till 2011, and then moved to IIT Madras. And then he has, continued his research program there with lots of students. So Sriramkumar and I go a long, long time back. We were both students around the same time. I mean, I was a bit senior to him then, and then he worked with very famous, physicist of the country, Professor Thanu Padmanabhan at the Indian University Center for Astronomy and Astrophysics. He held postdoctoral fellowships under very well-known names, Professor Jacob Bekenstein at the Raka Institute of Physics. For people who may want, pointed to Jacob Bekenstein, one of the things commonly he is very well known for is the black hole laws of thermodynamics. But besides that, he's been a leading figure in the field. And then he worked with Don Page, who is again quite a doyen in that field at the University of Alberta. And so I cannot imagine a more competent lecturer, and he loves teaching, and he does it also, regularly. So he's a very careful teacher. So please, take the most out of him. And he will give a set of lectures now on inflation, physics of inflation, and reheating. So without further ado, let me invite Sriram to start his lectures.
Thank you, Tarun, for a very kind and generous introduction. I should begin by thanking Tarun, Biman, Shiv, and others at RRI for providing me with an opportunity to visit RRI for extended periods of time. It's indeed a pleasure to be back here amongst friends. Over the last half a century or so, increasingly precise observations of the anisotropies in the cosmic microwave background has provided us with many clues to the physics operating in the early universe. During the past decade, the detection of gravitational wave from merging compact binaries by the LIGO, by the Laser Interferometric Gravity Wave Observatory, has opened up a new window to detect signatures from the early universe. In this series of lectures, my aim is to provide an introduction to inflation, which corresponds to a brief period of accelerated expansion during the early stages of the universe, and reheating, during which the energy from the scalar fields that drive inflation is transferred to radiation. This lecture today, this colloquium, is an overview, a compact overview of this series of lectures. In the first part of the talk, after a brief outline of the essential aspects of background cosmology, I will describe the need for inflation. I will discuss how inflation generates the primordial perturbations, and I will also discuss the manner in which the CMB constrains the inflationary models. In the later part of the talk, I will describe non-trivial dynamics during the later stages of inflation and during reheating, and how they generate primordial gravitational waves of strengths that can be detected by the ongoing and forthcoming gravitational wave observatories. At the very end, as a specific example, I will describe how the recent observations by the pulsar timing arrays, which suggest a stochastic background, gravitational wave background, can constrain certain aspects of the physics of reheating. Here's an outline of my talk. I'll just start with highlighting some aspects of standard model of cosmology. I will just cover those parts which are required for my discussion. And then I will describe inflation. I will describe how inflation is driven by scalar fields, how perturbations are generated, and how do you describe the perturbations? How do you characterize the perturbations generated in a typical inflationary scenario? And then I will talk about constraints on inflation from the Planck data and how it constrains certain inflationary models, but it does not constrain others. And later, I will very quickly share a small set of slides, just like how CMB provides a window to the early universe. Observations of gravitational waves, primordial gravitational waves, provide us a window to the very early universe. And I will describe specific mechanisms. I will describe this epoch of preheating, how it can boost the strength of primary gravitational waves. I will explain these terms as I proceed, how they can boost their strength so that they become comparable to the sensitivities of the various gravitational wave observatories. And I will describe, there are many other mechanisms. I'm going to focus on just two of them. And I will describe how, you can try to generate primordial black holes. These are black holes formed in the early universe. Maybe some of these have been seen by LIGO. And when you try to do so, what are known as secondary gravitational waves, you need to enhance the scalar perturbations on small scales. I will describe these terms as we proceed, how you produce scalar-induced secondary gravitational waves, or again, they can be of strengths that is comparable to the current and forthcoming gravitational wave observatories. And then lastly, as I mentioned, I will describe how nanograv data may possibly point to secondary gravitational waves generated by this mechanism I just mentioned. And then I will close with a brief outlook. A few aspects of standard model of cosmology. Well, we know there is matter present in the universe. Matter seems very clumped as we see all around us. This is a slice of the distribution of galaxies as observed by the Slow and Digital Sky Survey. It's very clumpy on small scales, but on a suitably large scales, it seems fairly evenly distributed. If you take a circle of radius of order of 100 megaparsec or so, and what one finds is that independent of where you place that circle in the sky, you find the same amount of matter within that circle, and you refer to this as the scale of homogeneity. On large scales, the universe seems homogeneous, and as we shall see, isotropic as well. And one of our first goals is to explain this level of homogeneity and isotropy. there is, apart from matter, there is radiation present in the universe. This is evident. We see radiation all around us. What has been plotted here is the spectrum of cosmological background radiation, and it has been plotted over a wide range of frequencies or wavelengths. But you see, it peaks in a very small region, in a small window of the electromagnetic spectrum, and this peaks in the microwave region of the electromagnetic spectrum. And this part of the spectrum has been zoomed in and plotted here. This spectrum is a famous spectrum by the so-called FIRAS, instrument aboard this Kobe satellite. And what it found is an amazingly perfect black body spectrum. And often, it should be emphasized that these error bars have been enhanced by 400 times or so that they are visible in this plot. So what you have is matter, and what you have is radiation, and radiation is in the form of a thermal distribution, and the temperature of this so-called cosmic microwave background means it is present everywhere. It comes to us from all regions of the sky, and it peaks in the microwave region of the spectrum, and it's cosmic, as we shall see. Now, you have matter in the universe, and you have radiation in the universe, and you will know that on these large scales, and at the greatest strengths, gravity has to be described by Einstein's relativity. So you combine them. There is another aspect which I haven't indicated here, but I presume you're all familiar with it. The universe is expanding. So you take into account the fact there is matter present, there is radiation present, and the universe is expanding, and you combine these together, what you immediately arrive is something called the hot Big Bang model. You can show at the very early stages of the universe, it is the radiation energy density which dominates rather than the matter energy density. So as this, screenshot from the title song of this popular Big Bang theory says rather, our whole universe was in a hot, dense state. It started in a hot, dense state. It cooled down as it expanded. And what you observe as the cosmic microwave background is essentially the remnant or the vestige of this, radiation from the early universe. What you essentially see is as follows. What essentially happens is as follows. There is a decoupling of matter and radiation. And thereafter, after such a decoupling, which occurs at a certain time, I will just indicate the time in a matter of seconds, the radiation starts streaming freely towards us. The yellow, smeared yellow here is the radiation fluid. And these large red balls are protons. The large green balls are neutrons. And the small green balls are electrons. And so essentially, this is a hydrogen nucleus, while this is a helium nucleus. And the universe, as it expands, it cools down. And there comes a time when there is not enough energy in the photon to knock off these electrons that are, trying to combine back to form a hydrogen atom or a helium atom. And this occurs at a, temperature of about 3000 Kelvin or so. Recall that the temperature of the CMB is about 3 Kelvin today, and the temperature was about 10⁻³ times larger than it is today. Early in the universe, what happens is that there is a decoupling. That is, the photons stop interacting primarily with the electrons, and these photons start streaming freely towards us, and which is what we observe as the cosmic microwave background. So this is roughly denotes the epoch of decoupling. And as you can imagine, it comes from all regions of the sky. And what you have is a large scattering surface. Very much in the same manner as a photon that travels through the clouds, it has a very short mean free path initially, but as it comes to the edge of the cloud, suddenly the mean free path becomes extremely large, and it starts, traveling and reaches your eye. What you have is a surface of large scattering. As you look at different regions of your sky, you have these epoch at which the photons decouple from matter, the photons stop interacting with the electrons, and they start freely streaming towards us. And that is what you observe as the cosmic microwave background radiation. And just as you can, project the temperature, say, on the surface of the Earth, the temperatures at different regions on the surface of the Earth onto a map such as this, you can map the CMB sky onto an oval-shaped map such as this one, and this is what you see in the various CMB measurements present. And this is one of the earliest measurements of what are known as the CMB anisotropies. I mentioned as to how the temperature of the CMB is about 2.725 Kelvin or so today, and it happens to be roughly the same at different in the different directions up to the 5th decimal place. But at the 5th decimal place and beyond, you begin to see differences in the CMB sky. Now, I mentioned earlier that the universe was clumpy, but we choose to describe it as a smooth and universe. And this CMB sky, which we observed during the early stages of the universe, is remarkably isotropic, which implies at the time of decoupling, it was remarkably homogeneous as well. So what cosmologists do is divide the study of the universe into a homogeneous part, which is what I'm trying to describe until now, and a perturbative part where these anisotropies arise. So the challenge before us is not only to explain the extent of isotropy, that is the same temperature in different regions of the sky that we observe in the CMB sky, and explain as well the extent of anisotropies, the type of anisotropies that have been generated on this smooth background. These are the, as I mentioned, the first detections of anisotropies by Kobe almost now 30 years back. And there has been increasingly precise measurement of the CMB anisotropies. And as you can understand, by examining the screen from which the last scattering surface from which these photons come to us, we can understand the physics that has operated behind the screen during the early stages of the universe. These are the anisotropies as measured by WMAP a decade and almost 2 decades back. And these are the measurements by Planck about a decade ago. So we are increasingly measuring the anisotropies to higher and higher precision. Now, the Big Bang model seems to be able to explain the presence of the CMB, and it seems reasonable to imagine that there will be some deviations from this isotropy or inhomogeneities in the early universe. But why do we need inflation? Well, there is a problem with the hot Big Bang model, and this is known as the horizon problem. So you have the epoch of radiation domination when the radiation dominated, and then thereafter decoupling occurred, and there is a transfer from an epoch of radiation domination and to the epoch of what is known as matter domination. There is a later stages of what is known as cosmological constant domination. We will not talk about this, which all forms part of the standard model of cosmology, but will not require for our discussion. You can ask, what is the size of the causally connected region at the time of decoupling? There was a finite time. I mentioned the temperature of this CMB at the time of decoupling. One of the exercises we will do as we proceed with the lectures is to calculate the time, and it happens to be about 380,000 years or so. And you can ask, what is the forward size of the horizon, the large causally connected region at the time of decoupling? And you can ask, what is the size of the, what is the angle that subtends today? So as you go back, as you look in any direction of the sky, you're looking as it was at an earlier and earlier epoch. You can ask, what is the size of the causally connected region, the forward region, at the time of decoupling? And that happens to be, this is an exercise we will do again, this happens to be about 1 degree or so. In other words, if the CMB had very different temperatures, which are separated by more than 1 degree, we would not have been surprised. This would have been perfectly plausible within the hot Big Bang model. But instead, what we find is that even antipodal points in the sky, points which are separated by 180 degree or so, have the same temperature. This is the horizon problem. The horizon seems to be very small. It should have been as large as this, 360 degrees, in order to ensure that the temperature of the entire sky, CMB sky, is the same. There is another way of stating this. We will examine what is known as the Friedmann-Robertson-Walker, Lemaitre-Robertson-Walker line element in something called the conformal time coordinate. In terms of the conformal time coordinate, though there is space-time curvature, the light cones, the metric is non-trivial. We don't necessarily need the space-time curvature. Metric is non-trivial. The light cones are at 45 degrees. You can ask, what is the forward light cone? Just invert this purple light cone, and it will be of this size. This is the time from which the CMB comes to us. We will talk about redshift in the lectures. I did not have the time to squeeze it in here. This is the time of decoupling from which the CMB comes to us. This is, say, the Planck or the CMB satellite, which measures these anisotropies today at a redshift of 0. And you can draw this forward light cone. It happens to be much smaller than the backward light cone. The vertical axis, something called the conformal time coordinate, in which the metric is conformally flat, and therefore the light cones go at 45 degrees. And you can show within the hot Big Bang model, it starts at, the Big Bang starts at a conformal time of 0 or something like that. Okay, and the forward light cone is finite, small, much smaller than the backward light cone. And this is the statement of the horizon problem. What you can do is, if you have an epoch of inflation, which essentially corresponds to an epoch of accelerated expansion, the conformal time coordinate can become negative. So if you have an epoch of inflation, you can push inflation, the Big Bang rather, as far back as possible, and you push it adequately back so that the forward light cone is as big as the backward light cone, so that the entire CMB sky corresponds. Okay, entire CMB sky corresponds to the horizon. Did I do something? I need to make this full screen. Just make it full screen. Will Control L work? Yeah, okay, thank you. So you can ensure that this entire region of the CMB sky is causally connected. And there is a similar way of expressing the horizon problem, and it is as follows. There are two scales in the when you study what are known as perturbations in the universe. What do we mean by a scale? Well, I mentioned we are going to study the universe, divide the universe into two parts, one which is a smooth background on top of which there are perturbations. And the perturbations, we will assume them to be linear. They will become non-linear, but we are in the early universe where they remain linear. And when there is a small perturbation about a smooth background, you can Fourier decompose, and where you can essentially reduce the partial differential equations to essentially complete differential equations, and you need to integrate each Fourier mode along in time. Okay, and that is what you do. And when I say a wavelength of when I say a wavelength, I'm referring to the wavelength of one of these perturbations in the Fourier space. And in a Friedmann universe, the wavelength of the perturbations are always proportional to the scale factor. The other scale that is available to you, as we will discuss, as you may already know, there is a scale factor. And you can construct something known as the Hubble time associated with it. And the Hubble time, you can construct a Hubble scale. Remember, C equal to 1, okay? And that corresponds to the Hubble radius here, which has been plotted in red. And what we will discuss this afternoon, that there is a certain scale, which leaves the Hubble radius as you go back in time at, various scales leave the Hubble radius as it go back in time. And specifically a scale of about what is known as 100 megaparsec that I mentioned leaves the Hubble radius. As you go back in time, it becomes larger than the Hubble radius at the time of decoupling, or more precisely at the time of equality, when the energy in matter equals the energy of radiation. Or in other words, in the hot Big Bang model, you can show what has been plotted is the logarithmic logarithm of this wavelength of these perturbations and logarithm of the Hubble radius, which we will denote as d subscript h. And you can show in the log plot, this n is essentially logarithm of a, often referred to as e-folds. And in this log plot, you can show this as a slope of unity, which is evident, while this has a slope of 2. And therefore, if you had only the hot Big Bang model, that is, you have an early epoch of radiation domination and nothing else, all the modes are outside the Hubble radius at a very early time, which means that they are essentially larger than the size of the horizon. We will talk about the differences between the Hubble radius and horizon in due course, okay? And it becomes larger than the size of the horizon, and therefore there is no way of inducing perturbations in a causal way in the early universe. But if you have an epoch of inflation, accelerated expansion, what essentially happens is the Hubble radius remains nearly constant, and therefore you have an epoch of inflation. These modes will be well inside the Hubble radius, and you can impose well-motivated initial conditions, as we will discuss very soon. What's the duration of inflation? Well, as I mentioned, inflation occurs during the early stages of the radiation-dominated era, at a time very close to the Big Bang. It is supposed to occur at a time of about 10 power minus 35 seconds. We will discuss, what is the range of time over which inflation can in principle occur. And in order to overcome the horizon problem, you need about, the universe to increase over a very short span of time. Notice this is the scale factor, or the size of the universe. Remember, the universe is expanding, and it is expanding slowly during the epochs of radiation domination and later during matter domination. But during inflation, it has to expand remarkably fast, remarkably quickly, and it has to expand by a scale of factor of about rather 10 power 26 or so in order to ensure that you overcome the horizon problem. That is, the entire region of the CMB sky is causally connected. But how do you drive inflation? You cannot drive accelerated expansion. This will become evident from the Einstein's equations applied to the Friedman-Robertson-Walker universe, which are called the Friedman equations. And you need to, you cannot drive accelerated expansion using matter, ordinary matter or radiation. You need to turn to exotic matter in order to achieve accelerated expansion. And what one does is that one turns to scalar fields that are abundant in high energy physics. And what essentially happens is that you have a scalar field potential. It is very much like a particle rolling a potential in classical mechanics, just that the expansion of the universe induces a friction term. And what we will talk about slow roll inflation, where the field is slowly rolling, you can assume the friction to be very small. So even if you start with a large velocity, the field slows down. And if you take, variety of trajectories, they will join this attractor and they will come down. Think of, as I said, a particle moving down a potential with friction. It comes down the attractor. Even if it initially starts with a large velocity, the friction slows down this the speed of the scalar field, and therefore you are guaranteed inflation. And that is why it's referred to as an inflationary attractor. I should have illustrated many different trajectories which join this trajectory, and it comes down and it rolls around the bottom of the potential. And inflation is supposed to end somewhere here around this location or so. And reheating occurs as the field oscillates at the bottom of the potential. We will discuss all these in great detail, and in particular, we'll focus on a very famous model originally due to Stravinsky. We talked about the background during inflation, but it is driven. We also talked about how inflation is driven with the aid of scalar fields. Scalar fields contain fluctuations. You have to treat them as quantum scalar fields in the early universe, which inevitably contain fluctuations. And you need to, it is these fluctuations in the scalar field that are responsible for the anisotropies in the CMB and eventually the structure and possibly you and me. And what we have are two types of perturbations. We will discuss in some detail the different types of perturbations. You will have scalar, tensor, scalar vector and tensor perturbations. Vector perturbations are not induced during inflation, but scalar and tensor perturbations are induced during inflation. The scalar perturbations are primarily responsible for the anisotropies in the CMB and, completely responsible for the formation of large-scale structure. And the tensor perturbations are essentially gravitational waves. And you can arrive at the action. We will not arrive at this action describing the scalar and tensor perturbations, but we will arrive at the equations of motion, which are of this form. Remember, I told you, if you have small perturbations about a smooth background, you can study them in Fourier space, where they will essentially become, complete differential equations, independent differential equations for each of the modes. And these are the modes that describe the scalar and tensor perturbations. And what we are observationally interested is something called the power spectrum, which I will come to. What you need to do is you need to solve these perturbations equations. But you need initial conditions for these perturbations, and quantum field theory in a curved spacetime provides these initial conditions. As long as you are in a domain, I had this picture earlier. Now we are looking at these different modes. You impose these well-motivated initial conditions when these modes are well inside the Hubble radius, what are known as the Bunch-Davies initial conditions, and you can evolve them. And I will just illustrate the manner in which the perturbations behave. What essentially happens is that at very early times, when they are inside the Hubble radius, they don't feel the curvature of space-time. They will very much behave like modes in a Minkowski space-time. As you know, the solutions to any field, free field in a Minkowski space-time, just oscillates. And as I will describe in the next slide, they will be oscillating initially. But as they cross this Hubble radius, essentially they begin to feel the curvature of space-time. And thereafter, they will not be oscillating. And we will see it freezes. So you have oscillations in the sub-Hubble regime as the modes leave the Hubble radius. At this time, it's called the Hubble crossing. When the modes leave the Hubble radius, they re-enter the Hubble radius at later times. We'll talk about that later. And as they leave the Hubble radius, their amplitudes freeze. And this is when you evaluate the power spectrum. The power spectra can be expressed in terms of the quantities that describe the scalar and tensor perturbations. We will discuss this as we proceed with the lectures. And conveniently, for comparison with the observations, we don't worry about the specific models and the type of spectra. We describe in terms of these quantities here, power spectra here, which are evaluated at late times during inflation when the amplitude of the modes are frozen. And what you do is that you introduce 4 quantities, what are known as AS, NS, AT, and NT. We still haven't seen the imprints of the tensor perturbation, so we are not so worried about NT. We are essentially focused on AT. We know AS so well, we don't worry about it. Okay, and what we are interested in, what is known as the scalar spectral index, NS, and the tensor to scalar ratio, R, which is essentially AT by AS evaluated at a particular scale. And this is what we try to constrain from the Planck CMB data. And just a quick word, this is something, people like Shiv and Tarun work on extensively. So these are the theoretical angular power spectra that are well-developed codes available today, given a primordial power spectrum to calculate the corresponding imprints on the CMB. And what these are the different imprints on the CMB through the temperature correlation. These are polarized. The CMB is polarized, and there are 2 types of polarization. One is interested in what are known as the E and B polarization. And what is important is that the B polarization is generated, even through scalar perturbations. And what you need to if you remove this lensing part, which is, because of the scalar perturbations, lensing the CMB photons, if you remove this part, what you see here on large scales is a pure imprint of the primordial tensor perturbation. And that remains the holy grail of cosmology. We have been able to measure the T. I think these are just the scalar perturbations. These are the imprints of the tensor perturbations. And this, as you can see, is much smaller than the imprint of the scalar perturbation, even for a large tensor to scalar ratio of 0.24 or so. Okay, and what one wants to do is, there will be a B mode, so-called B mode, due to the scalar perturbation through lensing, and one wants to, from the observations, remove this part and hopefully see the imprint of the tensor perturbations, which will tell us exactly what R is, and hopefully tell us what is the scale of inflation. This is, again, we will discuss during the lectures. This is the CMB anisotropies as seen by Planck. For want of time, I'll skip this, and I will talk about the constraints. What you are trying to constrain is the primordial scalar spectral index and the tensor to scalar ratio R. And this, we haven't yet seen direct imprints of the tensor perturbations. And that tensor, tensor to scalar ratio is constrained to be about 0.54 or 0.54 by Planck. And there have been improved measurements of the tensor contributions, and that remains the holy grail of cosmology, detecting the primordial imprints of the primordial B mode. This is the B mode, the so-called CLBB, but this is the lens part. This arises due to the scalar perturbations, and this is the upper limit that I talked about, arising purely from the tensor part. And there is a great effort to try to measure this. This constraint of 0.54 that I mentioned has been improved by taking into account data from the bicep Keck telescopes, and the current constraint on R happens to be about 0.36 or so. And this is the future prospects. Let me just take a sip of water. These are the future prospects. What has been plotted, focus on these red, blue, and green curves. They correspond to the pure primordial tensor mode corresponding to an R of about 0.05 or so. And this is due to lensing, all right? And this is the sensitivity for a light. This is the, for a light bird-like configuration. So if R is somewhere here, you will be able to detect its imprints, okay? And that's the hope over the coming decade or so. Various forthcoming missions such as LightBird, or even a mission that Tarun and co have proposed named ECHO to ISRO, may be able to detect the primordial tensor mode, and therefore identify the scale at which inflation takes place. Now, I talked about a nearly scale invariant primordial spectrum. I didn't emphasize this part for want of time. What we had is NS, which is like 0.965 or so. That is the best fit value. If you have recalled the manner in which I wrote the primordial spectrum, I wrote it as k power ns minus 1. Ns minus 1 is 0.035 or so. And therefore, you have a spectrum which is nearly scale invariant, but over a specific range of scales. We'll talk about this range of scales in a matter of minutes. So you have a spectrum which is nearly scale invariant. For a long while, Tarun and later Dheeraj and others have explored the possibilities of features in the primordial spectrum. This is again, we will discuss in one of the lectures, how to generate features in the primordial spectrum. And this, is the scale over which the CMB is sensitive to. Remember, the scale that re-enters the Hubble radius at the time of decoupling is about 10 power 2 megaparsec. That's here, 10 power 2 megaparsec inverse in K. And the CMB is essentially sensitive to something like 10 power minus 4 megaparsec inverse to about 1 megaparsec. And this is, in other words, if you want to correspond to it, to correspond to a inflationary potential, you're constraining a small piece of the inflationary potential. You need additional information if you want to constrain the entire inflationary potential. And what we have investigated is whether there are features in the primordial spectrum. That is, whether there are deviations from scale invariant. And what has been found is certain types of features improve the fit to the data. And one type of feature I will point to is something here, like this here, where there's a sharp drop in power and there is a rise and nearly scale invariant amplitude. We will see that we will consider such types of features at much smaller scales or much larger K in order to produce primordial black holes a little later in the lecture. So this is as far as the CMB scales are concerned. To emphasize the scales again, we are talking about scales of about 10 power minus 4 to about 1 megaparsec inverse. And we would like to understand, as I said, to not only on these scales, but on smaller scales as well. How do we probe smaller scales? This is where gravitational waves come in. Yes. I will talk about it. Okay. These are specific models which generate these features. Okay. And we will see a few slides later, about 8-10 slides later, how you encounter spectra of this type with some differences in shape, okay, to produce higher number of primordial black holes. We'll talk about it in a matter of minutes. So this, as I said, is supposed to provide an overview. I don't expect you to follow everything. We'll fill in the gaps. Whatever you don't understand, please ask questions. We'll fill in those gaps as I proceed with the lectures. So gravitational waves provide a new window to the universe. This is a famous picture from NASA. And what has been plotted, I hope you recognize, is essentially the behavior of the scale factor. And the universe has been, sort of captured in between to this, a reflection of the scale factor, the original scale factor and its reflection. And this evidently is the CMB. And you need this epoch of inflation. We really don't know what happened at the time of the Big Bang. Sometime after the Big Bang, there was an epoch of inflation that is supposed to happen, where there was a rapid expansion of the scale factor. Notice there is a slight change in shape indicating a late time acceleration. I hope you have observed that. And what we are interested in probing the physics of the early universe, and we have seen how the CMB provides a window to what happens behind this curtain. Well, gravity waves are able to probe even much earlier. They can, in principle, as I will illustrate, can probe, we can in principle see imprints of gravitational waves produced at the end of inflation. And in principle, we can observe what happened to them post-inflation on certain scales, on very small scales, as I will describe. And that is why the gravity waves provide a much more powerful tool than the CMB. Remember, the CMB photons stop interacting here. They are weakly interacting thereafter, and therefore they travel freely. The word that is used is free streaming CMB photons. They free stream to us until today. Gravity waves, because of their weak nature, they interact with matter very weakly, and therefore they in principle carry these imprints from the very early universe, which you can observe and try to in principle observe and constrain the physics of inflation and reheating. That's the goal. And I already mentioned as to how the quantum fluctuations that are generated during inflation can be observed a wide range of scales. Now we turn from K, which is the wave number. We talked in terms of megaparsec inverse. We will quickly turn it to hertz. It's a simple exercise for you to convert wave number into hertz. About 1 megaparsec is like 10 power minus 15 hertz. So the CMB corresponds to frequencies of about 10 power minus 16 hertz or so. And evidently, the quantum fluctuations which generate these tensor perturbations in the early universe can be observed from the CMB scales of about 10 power minus 16 hertz in frequency to any scale, even 10 power 9 hertz, gigahertz. And the LIGO that you have heard of, people who have talked about it, I'm sure, okay, corresponds to, operates at a frequency about 10 hertz to a few kilohertz, a few hundred kilohertz. And this is essentially picks up gravitational waves from merging compact binaries. In principle, it is sensitive to gravitational waves from the early universe. So the sensitivities of LIGO can, in principle, constrain the physics operating in the early universe. On the other extreme, as I already mentioned, is the cosmic microwave background. And there are space interferometers, LISA, for instance, which can constrain in the intermediate regime. And essentially, this picks up binaries during the very early stages of coalescence. LIGO picks up binaries during the late stages of coalescence. And more importantly, these pulsar timing arrays, which I will talk about a few slides later, are indeed sensitive to what is known as the nanohertz range of gravitational waves. Okay, and I will very briefly describe how the pulsar timing arrays try to constrain a background of gravitational waves. So, what are the physics that can affect the spectra of gravitational waves? The first is the physics of reheating. I had earlier plotted this. We talked about first inflation, right? There is an inflationary attractor. There is inflation happening until the field comes to nearly the bottom of the potential. Once it reaches the bottom of the potential, it oscillates. And what happens is as follows. During inflation, okay, the temperature of the universe largely goes as 1 over the scale factor. And during inflation, the inflaton or the scalar field that drives inflation is supposed to be dominant. All other fields do not affect the dynamics at all because their strength is not adequate. Their energy density is not adequate. So if there is radiation is present, it drops. The temperature of the radiation drops considerably. So it will drop by a factor of 10 power 30 or so, whatever the temperature at the start of inflation. By the end of inflation, remember, we need to inflate the universe by a factor of 10 power 26 or so in order to resolve the horizon problem. As we do so, we end up cooling the universe. In fact, the universe can, in principle, cooler than it is today by the end of inflation. So what you need to do to restart the Big Bang model, hot Big Bang model, which works well otherwise, we need to reheat our universe. And this is the phenomenon of reheating. What it does, there is one lecture where I will discuss the reheating mechanism. Okay, what it does is that at the bottom of the potential, as the field oscillates, it couples to the standard model fields of the standard model particles. Okay, and as a result, what happens is that this energy, this enormous energy that is available, potential energy that is available in the inflaton, is transferred to radiation, and this is the phenomena of reheating. And earlier, I had plotted, the evolution of the physical wavelengths. I talked about how the physical wavelength is always proportional to the scale factor, and I plotted this, the physical Hubble radius. It is essentially A dot by A inverse. Dot is differential with respect to cosmic time. A is, of course, the scale factor. And instead, what I have plotted is something called the co-moving lengths. It is something, these different pictures is something you need to get accustomed to as you discuss the physics of the early universe. What has been plotted is the co-moving lengths as a function of time and the wavelengths. Because we are plotting the co-moving wavelength, okay? So they remain constant. The co-moving lengths don't change with time. The Hubble radius, which was constant, okay, starts coming down. And if you had radiation domination immediately after inflation, it would have just had a slope of unity, like this here. So essentially, this corresponds to modes being inside the Hubble radius. They leave the Hubble radius and re-enter at later epochs. And during a period of reheating, what essentially happens is that there are a range of modes. This is the last mode to leave the Hubble radius during inflation. And this is the mode that re-enters at the end of reheating. So these wavelengths between KRE and KF can be affected by this epoch of reheating. Now, we don't know what happened at the end of inflation and at a later stage of radiation domination until the time of Big Bang nucleosynthesis, which happens at very small temperatures. We will talk about the exact numbers as we proceed. And if you had a second, phase of reheating, because some scalar field, suggested by string theorists becomes dominant, it can change this dynamics. And the change in the dynamics can leave its imprints on the gravitational waves. Okay, I'll skip this for want of time. So if you had just a period of reheating and you had instantaneous reheating where the energy from the inflaton was immediately transferred to radiation, what you will have, this is the energy density of gravitational waves today. Okay, I haven't introduced the definition, etc., because I will introduce them in the lectures. And have been plotted as a function of frequency. And these correspond to different reheating temperatures. If you had instantaneous reheating, then what will happen is that this primary gravitational wave, these are generated in the vacuum during the early stages of inflation, they will have they have a value of about 10 power minus 17 in these units, and they will remain scale invariant if it was instantaneous reheating. But if reheating was not instantaneous and there was a non-trivial dynamics during reheating, it will change the tilt in the primary spectrum of gravitational waves. And if omega during that period, okay, if the equation of state during that period is greater than 1/3, it will introduce a positive tilt, and they can in principle be observed by the various gravitational wave observatories. What has been plotted, I hope you recognize, are the sensitivity curves of the various gravitational wave observatories in units of omega GW h squared. Yes. The energy is transferred immediately. So the universe at the end of inflation, I told you that during inflation, the temperature comes down drastically. So there is some mechanism at the end of inflation which takes it back to the original temperature. So I will come to that. I'll come to that. Please ignore that, the BBN constraint. We will discuss that later. I don't have time to discuss this here. Okay. But if you had, yes. Or when you say instantaneous, we mean truly instantaneous. Of course, it is unphysical, but we are thinking of a situation and ideal situation where if it was instantaneous, it would have been straight. But it will not be instantaneous. In fact, there will be some detailed mechanism as these small bursts of oscillations indicate. Okay, but it depends on how well you can model the transition from inflation to radiation. Okay, all right. But if you had a second epoch of reheating, as I indicated, and of certain type, then what you can do is that you can boost the strengths of these gravitational waves, primary gravitational waves, which are generated in the vacuum during inflation. Remember, on the CMB scales at about, 10 power minus 16 hertz or something, R is constrained to be less than 0.036 or so. It is the same gravitational waves. We are talking at the other end of the spectrum. These are modes which are leaving inflation towards the very end of inflation. So in principle, these gravity wave observatories, had these epochs indeed occurred, could be sensitive to the, can constrain rather the physics operating at those scales. Again, I should emphasize, we have been talking about the constraints from the CMB on large scales. There are no such constraints on the scalar. Until now, we have talked about primary gravitational waves or tensor perturbations. Now we turn to scalar perturbations. As far as the scalar perturbations are concerned, the constraints are essentially over the CMB scales. There are additional constraints due to what are known spectral distortions and so on. We can ignore them for now. Okay. And at smaller scales, I'm talking about scales, let us say, even if you take into account spectral distortion, scales about K greater than 10 power 4 megaparsec inverse or so. Okay. And the inflationary scale will correspond to K of 10 power 4 megaparsec inverse to K power 19 or 10 power 20 megaparsec inverse. This is in frequencies, you're talking about something like 10 power minus 12 or so to about 10 power 9 in hertz. Okay, these scales are poorly constrained. We don't have any constraints. So the only constraint is that perturbation theory has to be valid. Perturbations seem to be small in the early universe. So in other words, what you have is as follows. I will talk about this and then I'll come back to those slides. So essentially, on large scales, you have some constraints from the CMB. That's here. This is, square root of the power spectrum. The power spectrum is about 10 power minus 9. Take a square root, it's about 10 power minus 5 or so. But on much smaller scales, scales greater than 1 megaparsec, you do not have any constraints whatsoever. In principle, I can have a power as large as 1. Okay. Often one works with something like 10 power minus 1, and it has interesting consequences. But why do you want to consider that? Well, I'm sure you have seen this picture. This is a picture of mergers observed by LIGO. And one of the strange things is that it seems to have some strange distribution of masses. And, before LIGO started observing this, astrophysicists didn't imagine that you will see, black holes in this range of solar masses. And one of the interesting things that could have happened is that these black holes were not astrophysical black holes, and that could have formed in the early universe. How do they form in the early universe? Well, it's as follows. This is another, simplified version of the co-moving plot of the co-moving scales that I had earlier. Remember, sometimes this Hubble radius is also referred to the horizon. I will talk about when they are equal and when they are very different as we proceed with the lectures. So these are the different co-moving wavelengths. This is the epoch of inflation. The physical Hubble radius is nearly constant, but the co-moving Hubble radius, which is essentially divided by the Hubble radius by the scale factor, comes down rapidly. And if you have an instantaneous reheating, you have an epoch of radiation domination. This has slope of -1, you can convince yourself, and this is slope of +1. We will discuss this. So modes leave the Hubble radius and re-enter. So if modes at late times, which leave the Hubble radius at late times during inflation, has very large strengths, okay, then as they re-enter the Hubble radius, you have these perturbations with enormous strength, and they will immediately collapse to form black holes. And these are what are known as primordial black holes. And if you want to have a significant number of primordial black holes, their strengths have to be very close to 1, and you don't want to touch 1 because you want to ensure perturbation theory is valid. How do you generate these models? I talked about inflationary attractor. You would have seen a picture like this earlier. Okay, earlier you had a straight line here, and it came down and it rolled down to the bottom of the potential. But something strange happens here. It comes down, the velocity almost comes down to 0, and then it somehow starts running again, moving again, and it comes down to the bottom of the potential end. So you have an inflationary attractor, as you can see. This is something I should have included in the earlier plot as well. Many trajectories come and join this, okay? But there are some potentials, which lead to something known as ultra-slow roll inflation. And this is one of the slow roll parameters, which I will introduce in a few lectures from now, okay? And it always remains small in some of the simple models that I showed. The Starobinsky model I talked about. Please remember this model. We will discuss this repeatedly. But there are models, when you have a point of inflection, what essentially happens is that there is a sharp fall in the first slow roll parameter, incredibly sharp fall in the first slow roll parameter. And that is what is reflected here. Rather, this leads to the sharp fall in the first slow roll parameter. There is a point of inflection. Remember, I told you a particle, the scalar field rolling down a potential is a particle falling down the slope. A point of inflection is where the slope vanishes, the derivative of the slope vanishes. So essentially, there is hardly any force on the particle, and it just stops there, and the scalar field stops there. Somehow, it retrieves, itself of the clutches of this potential and emerges to end inflation. And in fact, there can be a situation where inflation doesn't end, and the scalar field is just hanging around at this point of inflection. And in these slow roll, ultra slow roll models, these are not just slow roll. The first slow roll parameters drops exponentially. What happens is that the power spectrum will not be scale invariant, will not be smooth. What will happen is that the power spectrum will have a shape which is roughly like the slow roll parameter, but inverted. So it will have a shape like this, okay? And amongst this class of models, where you have epoch of ultra slow roll inflation, you have a subclass of models, which I have to highlight, okay, where around this, notice epsilon 1 rises, it almost, rises before it falls. there can be situations where inflation is actually interrupted for a very small period of time. These models, which are called as punctuated inflation, this is a name that was originally suggested by Tarun. It was in one of our early papers. And what essentially happens in these models of ultra slow roll and punctuated inflation is that, you have a rise in the power spectrum and it falls down. So you have a nearly scale invariant spectrum, which is supposed to be consistent with the CMB data. On small scale, there is a rise in the spectrum before it comes down. And this rise in the power spectrum, notice it's almost 10 power minus 2 or so. You can tweak such that it's almost close to unity. And what it does is that it produces a very large number of black holes. I need to take a couple of minutes to explain what I have plotted. What has been plotted is something called FPBH as a function of M. M is the mass of the black holes that have been produced. In slow roll inflation, the number of black holes that will be produced will be insignificant. It will be exponentially small. You need this ultra slow roll models or strong deviations from slow roll in order to generate strong features in the scalar power spectrum and therefore lead to enhanced formation of primordial black holes. What is this FPBH of M? It is essentially ratio of the cold dark matter. If you have black holes, they essentially behave like, cold dark matter. It is the ratio of the ratio of the energy density of black holes to the ratio to that of energy density of cold dark matter. Let me repeat that. It is the ratio of the energy density of black holes to the energy density of cold dark matter. And that's what this FPBH is. In other words, if FPBH is unity, you essentially can say that all the cold dark matter is in the form of primordial black holes. But there are constraints on primordial black holes or pockets of clump matter through gravitational lensing, like Matt chose, for instance. And these are the various constraints that have arisen. And these primordial black holes will evaporate, so they will not have very small masses. The smaller the mass, they will evaporate through a mechanism called Hawking radiation. Okay, these are the constraints. But in certain models, you can have, with some fine tuning, you can have primordial black holes formed at certain ranges, which are close to unity, if not unity. And in fact, it's much easier to generate them in two-field models than single-field models, but that'll be for story for another day. But something interesting happens. This is, again, I'm going to narrate a story, and we will try to discuss the details of the math in the lectures. I talked about primary gravitational waves. But what essentially happens is that any perturbations can, in principle, generate gravitational waves. So when you try to enhance power, scalar power, to this large values, what essentially happens is that there is what is known as anisotropic stress in the scalar perturbations, and they induce gravitational waves. And the gravitational waves they induce are much larger than the gravitational waves originally produced from the vacuum during inflation. This is the amplitude of the gravitational waves produced during inflation. Okay? And this is the amplitude of the secondary gravitational waves. I talked about strength of the gravitational waves earlier. This is essentially the spectral density of gravitational waves. In other words, the energy density in the gravitational waves at a given wave number. The primary gravitational waves strength will be like this. If it was only slow roll it will be somewhere here, 10 power minus 17. That is what I had earlier. If it was secondary gravitational waves and you had only slow roll inflation, no peaks in the power spectrum, then the secondary gravitational waves will be at a higher order. Therefore, they will be smaller than the primary gravitational waves. That's why they're called secondary. Okay, they will be at 10 power minus 23 or so. So if you had slow roll inflation, and this will be the strength of the primary gravitational waves we talked about earlier, and this will be the strength of the secondary gravitational waves. Secondary gravitational waves induced by the scalar perturbations. But we have enormous power on small scales now. As a result, what happens is that the secondary gravitational waves exhibit a peak. The larger and wider the peak in the scalar power spectrum, the larger and the wider is the peak in the secondary gravitational waves. And I hope you have recognized now that these different colored objects are the sensitivity curves of the various gravity wave observatories ongoing and forthcoming. And you can see that the gravity waves generated in these scenarios are indeed comparable to these curves. Now, in the remaining 7 odd minutes I have, I will talk about the nanograv data. This is, remember, there are different regions of the gravitational wave spectrum, which are to be observed by different detectors. These are not quite detectors in the sense of LIGO or LISA. These are essentially radio observatories, which are observing signals from pulsars. But because of the fact, if there is a gravitational wave background, they will affect the propagation of the electromagnetic waves. I can correlate the signals from different pulsars and try to constrain the type of gravitational wave background that is present. There is only one assumption that goes in. We assume it is an isotropic gravitational wave background. It is coming from, it's the same from all directions of the sky. So you construct what is known as a timing residual. So you have the pulsars emit pulses at specific intervals of time, okay? And you calculate the average time period, and you talk about the deviation of a given time period from this average, okay? And then you integrate over time from some initial time, okay? So you will hear that nanograv have been observing these pulsars for about 15 years or so, okay? And you integrate that. And what you do is that you observe with one pulsar, you observe with another pulsar and cross-correlate them and correlate across many pulsars. And this timing residual that one is interested in consists of two parts, okay, which is, purely dependent on the pairings of the pulsars, okay, all right, and another part which is sensitive to the primordial gravitational waves. Okay, there is a universal form, it can be decomposed into two forms. One, which depends on the nature of the stochastic gravitational wave background. And as you can imagine, for simplicity, we will assume the stochastic gravitational wave background as a simple spectral shape, like a power law form. Okay, it will be characterized by an amplitude and a spectral index, like the primordial power spectra we talked about. Okay, and then there is a part which is called as the Hellingsdown curve, which is of this form, okay, which has this shape, and that is universal, and that just is based on the assumption that the origin or the stochastic gravitational background is isotropic. And what are the constraints by the PTA data? They have seen a signal of a stochastic gravitational wave background. They don't think it is noise. They have been able to handle the noise, and they believe they've seen a stochastic gravitational wave background. And what we are interested in trying to understand, what is the origin? Could it be primordial gravitational waves generated in the early universe? These are the constraints on the A and the gamma. And there can be other sources. I will talk about a variety of sources very briefly, okay? And one of the competing sources is, this was appeared in my earlier slide, these are merging of supermassive black hole binaries. And they will emit in this nanohertz range of frequencies, and they will have something like this, okay? They will have an index something like that, okay? And what PTA has observed seems to be different from that. I should caution that there are assumptions about the distribution and the manner in which these SMBHs merge and the kind of gravitational waveforms they generate. Okay, and they are trying to fine-tune that as we speak. But one can try to understand whether primordial physics can explain this data. And what one finds is as follows: there are many possibilities. Everything that's moving in the early universe, any phase transition, anything can generate gravitational waves. And they have, this nanograv collaboration has estimated the Bayes factor when compared to the SMBHS model, the gravitational waves from merging black hole binaries. And what one finds is that SIGW stands for scalar-induced gravitational waves, which is what I talked about earlier. And if it has a Gaussian form, that is, the power spectrum has a log normal form to be precise, what you find is that it has a significant Bayesian evidence. In other words, such spectra, like those generated in ultra-slow roll inflationary models, seem to be able to explain the data very well. There is one assumption that we have made when I showed the omega GW. We have assumed all the modes re-entered the Hubble radius during the epoch of radiation domination. That is, we have assumed instantaneous reheating. But if you have an epoch of reheating, you can let those modes re-enter the Hubble radius during the epoch of reheating. And if you want to ensure that these range of frequencies that lie in the nanohertz range of modes, okay, are entering during the epoch of reheating, you need a very low reheating temperature, just above the reheating temperature of BBM. So you make these assumptions, okay, and what you need to do is that you have a nearly scale invariant spectrum on large scales like the CMB scales, and you have a spectrum. You saw that it went up like that and came down, and you can show in single field models that have a universal form, it has a K-power 4 form and it falls down after the peak. And you can use such spectra, and you need, I don't have time to discuss this, we will discuss during the lectures, and you can try to ask whether such spectra, and when those modes re-enter the Hubble radius during the epoch of reheating, can fit the data very well. And what one finds, I will skip this for want of time, okay? What one finds is that they indeed fit the data much better. This is the curves. These are the data with error bars, and these are different models. I don't have time to go into them, okay? And what one finds is that this model, this purple one with delta, this purple solid or purple dash line, long dash line, in fact, fit the PTA data much better than this competing SMBHS model. So, and you can arrive at constraints. And what is interesting is that these models can constrain what is known as the equation of state parameter during reheating. One assumes that the reheating is of a simple form. It is described by a single equation of state, and they can, in principle, constrain the epoch of reheating. And as more data comes in, one hopes such analysis can help us understand the physics of the early universe. And I will close with a quick outlook and a summary of the lectures I'm going to, topics I'm going to cover in the forthcoming lectures. The increasingly precise observations of the CMB by future missions such as LightBird, okay, or PIC-C, or ECHO, which is a proposed Indian effort, can help us improve the current constraints of the primordial correlations. This is on large scales. The observations by LIGO are a culmination, as you know, of almost 50 years of effort, and they have opened up a new window to observe the universe. The observations by the PTA and their possible implications for the stochastic gravity wave background offer a wonderful opportunity, as I illustrated towards the very end, to understand or constrain the physics operating in the early universe. Over the coming decades, observatories such as LISA, which is space-based, and Einstein Telescope and Cosmic Explorer, which are ground-based, can be expected as to provide us with an unhindered view of the primordial universe. Over the next lectures, next set of 11 lectures, I hope to expose you to these topics, if not help you completely understand, okay? So we'll start with, essentials of the Big Bang model and why we need inflation. We will essentially put numbers to all the story I told this morning, or rather just now, okay? And then we will talk about how you can achieve inflation with scalar fields. Why do you need 10 power 20, etc., and how do you achieve them? And which region of an inflationary potential do you need in order to achieve that? And we will start talking about perturbations, and we will set up perturbation theory. We will arrive at the equations that I mentioned. And then we will talk about the origin of the primordial perturbations. How are they generated? It's one thing to understand their evolution. You also need to understand their origin. And then we will talk about constraints on slow roll inflation. How I showed you how NS and R are constrained, okay? And we will talk about that. And I will discuss how you can generate features in the primordial spectrum. There are many types of features, so you need different types of deviation from slow roll to study them. We will discuss at least a couple of models. And then I will discuss the epoch of reheating. It is easy to discuss the evolution of primary gravitational waves. These are the gravitational waves that are generated from the vacuum, okay? That plots with, tilts in the spectra is easy to arrive at. We will discuss that. And then, we will discuss observational imprints of enhanced power on small scales. This will involve lengthy discussions. I will try to squeeze in as much as reasonably possible, okay, as much as possible. And time permitting, I will discuss about what is often referred to as the quantum to classical transition of the primordial perturbations. The perturbations arise in the quantum vacuum But what we observe are supposed to be classical perturbation. How did this transition occur? This has been studied extensively, but a complete picture has not emerged. What I will do is that I didn't use the word quantum to classical transition. We don't understand that yet. We can certainly understand how the quantum state associated with the perturbations evolved during inflation or even after inflation. That's roughly the scope of my lectures. Thank you very much for your attention, and I will be glad to answer some questions.
Okay, so before your question and answer session, because this was, what he would be taught at a pedagogical lecture series, plus his most recent research. So it was a colloquium come talk. So I hope people realize that most of what has been told will be gently expounded over in the next lectures. So don't get too worried about, oh my God, what is this going to lead to, So I would like to, sort of thank Sriramkumar for, taking on this, lecture series. This is an area which is, as you see from the things that he's talking, it's getting more and more exciting, rich with various possibilities. And I hope many of the young people here uh, would get exposed as well as learn some of the basics so that they can take it forward with, a lot more clarity on what the issues are. So on behalf of Raman Research Institute, I would like to present Sriram Kumar with pictorial biography of C.V. Raman. And also, the excellence here is not just Raman, but over the years, 75 years, a lot of interesting research has happened. And the highlights of this research are there in this Nature volume. And people should look at that. And
Thank you.
Thank you
Thank
so
you
much,
very
Sriram. So, yeah, I didn't want to interrupt the
Sure.
question answer. And
Sure.
thanks a lot.
Pleasure.
Thank you. We'll, for want of time, have a brief Q&A session with 1 or 2 questions, and then we will anyway reconvene here at 2 o'clock. So 1 or 2 questions here.
Hello, sir. So, I mean, you're talking about the scalar fields during the time of inflation. So, of course, the scalar fields will have a sort of back reaction on the metric in the sense that there will be some non-trivial curvatures on top of the Friedmann-Lemaitre metric.
If it is a homogeneous field, okay, there are 2 things here. We will divide the study, as I mentioned, into a homogeneous part and a perturbative part. So the homogeneous part, we take everything into account. The perturbative part, we assume it to be linear. So in some sense, you don't have to call it as even back reaction. It is the scalar field that drives inflation.
Yeah.
Okay, there is nothing. All the other fields that are present, all the other matter that are present, their energy density is so subdominant, they don't influence the dynamics during that period. Okay. And then on top of which, there are perturbations. And we will account for it. And in fact, those are responsible for you and me.
Maybe one more question, quick question. If there is none, okay, last question.
So there's this other hypothesis of cosmic strings also that could explain this stochastic background of gravitational waves. So such a statistical analysis, as you showed, that compares the 2 hypotheses, has that been done for that third?
Yes, there are many sources of gravitational waves. In one of the slides you saw, there are many possibilities. Okay, I haven't examined. There will be sources of strings which are forming in loops and cutting each other and so on. And the distribution can generate gravitational waves. And I am not able to say offhand what will be this. There will be phase transitions in the early universe which will generate. Each of them have their shape. And in that particular slide, I think if I recall correctly, there were various possibilities. Okay, I don't even know all the names. There are many possibilities here. Okay, and interestingly, for my story, okay, there is a particular type of gravitational waves, source of gravitational waves, which seem to fit the data very well. Okay, but all these are these are early results. There is a lot of excitement. There is early results, and there are many possibilities. So I will not be able to talk about strings or phase transitions. I'm not on top of it, but we will talk about the primary in some length. It's easy to do. And we will talk about secondary. It involves some math, but we should be able to achieve.
Okay, with that, we will conclude this session. Few logistical announcements. We know that there are few questions on Zoom as well. We will try to get back to you online when time permits during the course of these lectures. All the lectures will be held in this same auditorium, and lunch is organized in the Astro Floor Terrace. So that is basically the library block building, the top floor, terrace floor for the in-person participants. We will convene back at 2 o'clock this afternoon.
Thank you.